So I want to show you this equation. It's pressure is force over area. We're going to apply it to the setup here. And I want to find out how much pressure, air pressure, I need to apply to lift this 50-pound weight. So this is what is this called? This is a kettlebell, is it? Yeah. This is a real 50-pound weight. Trust me, I have a hard time lifting it. And we have a little cylinder here. I want to see how much PSI I need to throw into the cylinder to lift the weight. Okay? So if you look at P is equal to F over A, the weight, the force is going to be 50 pounds. So we just get rid of that. Now, the area in this example, this is a double acting cylinder. And what we're trying to do is lift this. So, and it's pretty heavy. So we're retracting the cylinder. So the area that we need to calculate is the area of the piston minus the area of the shaft. Okay, so it's this donut shape we're trying to calculate. That's our area. So the area is going to be, the total area is going to be pi r squared 1 for the big one, and then pi r squared 2. So pi is going to be 3.14 multiplied by, now what's R1? R1, now I know the cylinder diameter is 1.125. It says it on the cylinder. And then the shaft diameter is 0.375. So R1, these are diameters. So R1 is going to be half that. It's going to be 0.506, something like that.
565.
What is it?
0.565.
Good man. 0.56. It's good enough for me.
Yeah.
Squared minus 3.14 multiplied by
0.19.
0.19 squared. Right. What's 0.56 squared? So it's 3.14. What is it again?
The square, you said 0.31.
0.31 minus 3.14 multiplied by 0.19 squared.
0.036.
0.036. Right. What is 3.14 multiplied by 0.31?
0.9734.
What is it?
0.9734.
No, that doesn't seem right. 3.14 multiplied, you're right, 0.97, we're multiplying. 0.97 minus, what's 3.14 multiplied by 0.036? 0.11. What is 0.97 subtracted 0.11?
0.86, right?
Yeah, 0.86. All right. That is our area, 0.86.
That's square inches or what?
That would be inch squared, yeah. Okay. So, that's 0.86 in here. What is 50 divided by 0.86?
58.1.
So it's roughly 60 psi is what we need to get to. All right. Now, what is 60 psi in bar? Can you get that conversion for me? Let me see if I can see. No, it's all good. I can see it.
Around 4 bar.
It's around 4 bar. What's up, Victoria?
Hi.
Come here for come here for a sec.
Me?
No, you're good. Scott, come here for 1 sec. All right. So right now, I'm going to leave this at, now don't get too close to me. Bloody pandemic. What have I got this now? I have this at 30 psi. Are you watching? Now, back off now. You're going to love this. Hey Victoria, 50-pound weight, you see it?
Yeah.
Do you think the cylinder can lift it?
No.
No? Let's have a look. You ready? Okay, so no good there, right? So I have it at 30 psi. I'm going to crank this up a little bit higher. I'm going to put it in between the middle. Let's make it. Is that compressor even on? No, we're not getting a whole lot of pressure. Hold on a sec. Didn't even have the air turned on. Alright, hold on a sec. Let's bring that back down to 30 and see does it do it again. 30 psi, you ready? Yeah, not a hope. Okay. I'm going to bring this to about 40. I have that at 3 bar. Okay, you watching? Now I'll bring it to 60. Did it lift the weight?
Yeah.
Yeah. Not a bother on it. Okay. So, trust the maths. E is equal to F over A. That's it. Hey, this is Tim again. I hope you enjoyed that demonstration in our lab. I put it to the front of the video because I thought it was more interesting than this lecture, but I'll do my best. Before we get into Pascal's law and pressure and force and area and all that, I just want to go over some relay concepts that we covered last week. This is a logic diagram and electrical logic diagram, and you're going to have 24 volts on the left hand side and you're going to have 0 volts on the right hand side. Now, hopefully this doesn't look like hieroglyphics to you, but we have a stop button, we have a start button, and we have a relay. Okay, now this is what you're seeing here is a very, I wouldn't say it's famous, but it's used a hell of a lot in PLCs and pneumatics. This is a latching diagram. This is a classical latching diagram. So it would be an understatement of mine to say that you need to understand this. That's an understatement. Okay, so let's get into it. The stop push button is normally closed. The start push button is normally open. Hopefully you're aware that this is the coil of the relay 1, and this is the contacts of the relay. So let's look what happens here. So if I push this push button down like so, power comes across to the coil. The coil will close the contacts of the relay, which closes these contacts here, and you can actually, this can be a momentary push button. So I can lift this up and the circuit still remains latched or energized. So current comes all the way down here and through here like this, and it keeps it energized. Now, how do we break that then? If all of this remains energized, the one way we can break this is open that push button. Open up, we can press that stop push button, and that will kill power to that whole circuit. What we can do down here then, once this coil is energized and those contacts are energized, we can do stuff like this. we could have a pair of contacts here, and we can call this 1C, forgive my CRA, and what we can do is we can turn on, you know, we could turn on lights. What does this look like? A solenoid, or we can turn on like a motor here, down below. So this is a latching circuit. These are both momentary push buttons. Once you press down on the start button, it energizes this coil, which closes the contacts. It latches this circuit and it stays on. So you can see down here. So we have the same circuit up here, and what we're doing with this this control relay, we're using the other pair of contacts on the relay to like turn on whatever, a solenoid. We could turn on a light. We could turn on a motor. We can turn on whatever you want, a fan. So you're probably thinking to yourself, like, what is this is a latching circuit. So you're probably thinking to yourself, well, why do we go to all this trouble when we could have a D10 switch? Yeah, typically in an electro pneumatic or a PLC or an automated system, you need to have your own stop button. You cannot. It needs to be really clear. You need a start button and a stop button. Honestly, I'm guessing, and I'm throwing a guess here, that there's an NEC or there's some sort of electrical standard that says that a stop and a start have to be, they have to have separate buttons. But look, I'm not 100% sure there. So let's have a look at, let's see what's going on. Let's look at this electro pneumatic diagram here. So what's going on? What happens? This section here on the left is the ladder or the logic diagram. This on the right hand side is the power or the pneumatic diagram. We have a 4-2 valve here that is energized with a solenoid on one side, and it has a spring return. We have some flow control here, you know all that, and then we have a double acting cylinder. When this gets energized, it comes out and it hits a limit switch. Okay, so what happens? We energize the start button. We press the start button. Excuse me. Power runs across. This is 24 volts. This is 0 volts. Electricity runs across here. It energizes this coil. That coil gets energized on the relay. Once that gets energized, this contacts close on the relay, and the solenoid gets powered. This solenoid gets powered, and this directional control valve switches, and this block moves over, it shifts, and air pressure goes from P to A. Okay, and it goes through the throttle valve. This cylinder extends, it hits the limit switch, and what happens? What happens to the limit switch? The limit switch opens, it breaks the coil, the solenoid is de-energized, the spring comes into action, and now pressure goes from P to B, pushes the cylinder back, okay, breaks the limit switch, and that's it. So this is what's happening here. This is just it. We press the start button, the cylinder comes out, hits the limit switch, and comes back. So this is just a momentary button. at any stage of this operation, if the stop button is pressed, the cylinder will retract. So that's it. That's a pretty, I think it's simple, but there's a fair amount going on step by step. If you can understand that electro pneumatic diagram, that's a good state of affairs. That you're in good shape. Okay, so if this is melting your head, you're going to have a very, very difficult time with the lab this week. You need to go back over the lecture. If you're having a hard time with this, my brain is telling me you did not go over last week's material. Okay, you did not even look at it. So make sure you do. So now we're going to move on to Pascal. This lovely equation: pressure is force over area. So we're going to talk about Pascal's principle. He's a French scientist. He's dead, but he came up with a good idea. He came up with this concept of pressure. Have you ever seen people in the gym and they're lifting hundreds of pounds of weight? So they're sitting back and their legs are doing all the work, and they're lifting nearly 1,000 pounds of weight. So you're driving your car, and we have a cylinder here with a piston, and you can easily apply a force. Let's say you're a weakling like me. We can easily apply 50 pounds of force with our foot. Now imagine we have a cylinder here that has a 1 inch squared cylinder. Well, that would tell you, well, how are you supposed to know this? But if P is equal to force, pressure is equal to force over area, which I covered in that little demonstration before, we know that we can produce 50 psi. I lost my document camera, so you're going to have to suffer with my text on the screen here. So by pushing this lever in, hitting this piston, we're producing 50 psi in this fluid system, and we have all these brake lines or tubes going all over the place. But Pascal said, if you can generate 50 psi in this enclosed system, because this is a fluid, we have 50 psi here, we got 50 psi here, we got 50 psi all over the shop. Okay, and that's useful because we can transfer force to all these other places. So by applying 50 pounds of force to this master cylinder, if these these are going to the back brakes of your car, and these are going to the front brakes of your car. So when it's time to slow down, these brake pads, if the piston size is the same in each of the cylinders, well then you can apply 50 pounds of force to your brakes. So I'm after stealing these slides here. Pressure exerted by a confined fluid acts undiminished equally in all directions. That's pretty hard to get your head around. So fluids cannot be compressed like air. You can't compress a fluid and make it smaller in volume. That's what he's saying. So P stands for pressure. PSI, pressure, pounds per square inch. You have F is pounds, and A is inch squared. These are the units that we're going to use. Okay. So units of force per unit area. So if I wish I was 150 pounds. So 150 pound man standing on shoes with an area of 30 inch squared, 30 inch squared, puts a pressure on the floor of 150 divided by, so let's just write this down, P is equal to force. Let's not use me as an example. So the force is 150 pounds. The shoe area is 30 inch squared. So what are we getting? 5 psi. I tried to look up how much pressure is needed to break through solid ice, and I found some rough numbers. Okay, so anything over 3 psi will break through a 1 inch thick solid ice. They're the numbers that I found. I could be wrong, but so this poor chap is applying 5 psi. It's greater than the 3 psi, and now his ass is all wet. Okay, so what can we do to make sure this doesn't happen? We need to increase this area. He's 150 pounds, he ain't gonna change that, but what we can do is we can increase this area, and we can give him a pair of skis. Okay, so a pair of skis, the total area of a pair of skis, and how can you can calculate this distance here, which is, I'm guessing, about 3 inches, and then the length, which is going to be 125, 30 inches, 40 inches, okay, in length. So the total area, this total area of a pair of skis is 250. Hold on a sec now. How do I write with this bad boy? Is 250 inch squared. And what we're going to do is we have P is F over A. 150 divided by 250 is going to give us 0.4 psi. So this is a lot less pressure than the breakthrough pressure, so he doesn't fall in. So hopefully you understand. Hopefully you understand what pressure is. You have some concept of it. Now, there are 3 pressures that you might see. In my experience, I've only ever dealt with gauge pressure. Okay, it's the pressure on your pressure gauge. It does not account for atmospheric pressure on all sides of the system. At absolute pressure is your gauge pressure plus atmospheric pressure. Now, atmospheric pressure is 14.7 psi, but that would depend on your height above sea level. Forget about that. So get absolute pressure. So if your gauge is saying 50 psi on your pressure gauge, 50 psi, and somebody, I don't know why they would, but let's say somebody asked you, well, what is the absolute pressure? You would just add 14.7 to it, which would give us 64.7 psi. Gauge pressure uses atmospheric pressure at its 0 point. As its 0 point. So what you're going to see in industry is just gauge pressure. I don't think you're going to see this a whole lot. So I suppose what I'm telling you is, don't worry about it. If a gauge reads 120 psi, what is that absolute pressure? It's 134 psi. If some idiot in a job site tells you absolute pressure is whatever, you're just going to subtract 14.7 and you're going to get whatever your gauge pressure is. I've never nobody has ever told me about absolute pressure. We always just talk about gauge pressure. All right. Okay, we're going to do a couple of examples. I have I have a cylinder, and we've always applied a pressure to the cylinder, and we've always thought about its force, but it works in reverse. If we could apply 50 pounds to the piston, the 50 pounds pushes the piston in this direction. If the cylinder has a diameter of 3 inches, how much pressure am I going to get out here? Okay, what's my pressure here? How many psi can I produce? And this is what we can do. We know that pressure is equal to force over area. Forgive me with this crap writing. Let's calculate the area. The area of a circle is pi r squared. Now, so this is going to be equal to pi 3.14 multiplied by 1.5. I'm dividing this number by 2 as I want the radius. Squared. Oh my god. Alright, let's try this calculator. Alright, let's have a look. 1.5 squared. Alright. Now, I'm going to just double check that because 1.5 multiplied by 1.5, 2.25 multiplied by 3.14 is 7. Gives me 7.065. What a pain. Inch squared. Alright, and then I have P is 50 divided by roughly 7. 50 divided by 7. I'm going to get 7.14 psi. psi. So let's have a look. Let's have a look at another example. We have a pressure gauge. We have a direction control valve here. We have a double acting cylinder. Believe it or not, the double acting cylinder can extend and it can retract, and it's going to be able to apply different forces. The extension force is going to be higher than the retraction force. Why is that? Well, look, let's do it, and we'll see. The area. If I could chop this cylinder in half with a hacksaw, you would see that the piston looking in from this direction is a disc shape. Okay, and we calculate that whole area. That's how much. That's the area that we're going to take into account. If we look in from this direction, the retraction, it's not a disc anymore because you have a disc that's connected to a shaft. Okay, and the area that we take into account is the disc minus the shaft area, and we have a donut area which is less than this. Okay, so this is going to be the extension area. This is going to be the retraction area. So I'm going to have to write really small. So pressure is equal to force over area. Now, and we're trying to calculate how much. We want to calculate the extension force with little f, and we want to calculate the retraction force. going back in this direction. Now, so we need to calculate two areas. We're going to calculate the EA, which stands for extension area. There's probably a better word. The cylinder extends, the cylinder retracts. And what we'll do is we'll go pi r squared. Okay. 3.14 multiplied by 7 is going to be, we're going to half that, 3.5 squared. 3.5 squared multiplied by 3.14. So we're going to get an area of 38 inch squared. Okay. Now we're going to use that later, and then we're going to go. Let's get the area of the shaft, or the air. Why did I write that? The extension area. Okay, so let's do this. Let's go shaft area. Is pi r squared. And we don't know that. Is that dr dp retraction? The area is retraction 2. I don't know what this means. So if this is 7, we will say, if that's 7 inches, we'll say that this is 2 inches. From there to there, 2 inches. Okay. So we're going to have 3.14 multiplied by, we're going to divide that number by 2, so that's going to be 1 squared. Lovely, I like it. Which is just going to give us 3.14. So we will say, so the area of this is 38 inch squared. That's a pretty crappy looking 3. Let's try it again. Here we go. And then the area of this donut is going to be 38. Oh, that's really 38 minus 3.14, 35.3. Okay, 35.3. Now, P in this example is F force extension over A. P is force RET over A. Now, P is 124, and we're going to bring this over to multiply it. Now, what is this A in this example? It was the 38 is equal to force, come on Tim, extension, and that's 124 times 38, which is 4,712 pounds. So force is 4,712 pounds. And then the pressure in this example, so if we had a door that was 4,000 pounds in weight, this could push it out no problem. And then what do we do here? We go, P is 124 in this example, 124 multiplied by A, which is 35, is equal to the retraction force, F, or, so what is it? 124 multiplied by 35, 4,340. 4,340 pounds. So what a pain. Right. The last thing we're going to do is we're going to do a few more example questions. In the United States, we like PSI. Everyone else use bar. Okay. I haven't heard Pascal, a pressure of Pascals being used too much. So whenever, if 1 psi is equal to 0.0689 bar, I know that 4 bar is enough. Anything over 4 bar is a little bit dangerous in the lab, and I know that's pretty close to around 60 psi. So let's see what 60 multiplied by 0.0689 4 bar. Okay.